Welcome to Unlocking Science. Our goal is to glorify God by studying and unlocking the mysteries of His amazing creation. I'm your host, Mr. P, and I'm joined today by Dr. David Menton, Dr. M, I guess. Yes, and we're going to be talking today about the heart. And what qualifies you to be talking about the heart?
Well, I taught in a medical school for 34 years in the Department of Anatomy. So I've had my hand in the dissection of a few hundred cadavers. My primary teaching was a course called Microscopic Anatomy, or Histology, looking at the world through the microscope.
Mm-hmm. So you've not only understood the gross anatomy, the whole structure and the way everything works together, but also the fine details, looking at the cellular level of all of these things.
Right, from the gross to the ultra microscopic through the electron microscope.
Yep. And as a reminder, when we say gross anatomy, that means the large structures and the way things are organized, not that it's gross. Some people might think it's gross to be talking about hearts and pieces. So today we're going to be focusing on the heart, and then we get to do other programs focused on different systems of the body. So we'll follow this up with circulation and other things. And this is all kind of part of, we've recorded a series of DVDs of yours called The Body of Evidence Talks. So a lot of that information is available in those as well. So this is a great resource for families to get to use as an educational tool to train up your kids and help them understand how all of the body systems work. Great resource. All right, so we've got a few models here today. We're going to be working with this stand-up model over here to look at where the heart is and some other pieces, and then this heart. Now, this is a pretty big heart.
Yeah, that would be about 3 times bigger than it ought to be, but that's for educational purposes only.
Yeah, all right.
But you know, a heart could be almost that big. I've seen hearts pretty close to that. Raises a whole question: how big should the heart be? Well, you can pretty well see how big your heart is if you just close your fingers into a fist and put your fist right over your sternum here. Your heart is in that position and is about that size. But the heart can get a lot bigger. I wonder how many in our audience can think of some reasons why a heart could get much, much bigger in an individual than this normal fist size.
Mm-hmm. Now, this is a pre-recorded show today, so we'd normally be able to take some answers from our audience with that, but we won't be able to do that today.
So what would make the heart get bigger? The heart is mostly muscle. It's a ball of muscle, really. And it's a special kind of muscle called cardiac muscle. There are 3 types of muscle in our body. Smooth muscle, like in the intestines, uterus. We usually don't have control over that. We have skeletal muscle that we use to move our arms and limbs around, legs. That's attached to our skeleton. And then there's cardiac muscle, found only in the heart. And cardiac muscle has one interesting property. It can contract without any outside signal or stimulus. So even individual heart muscle cells growing in a dish will actually contract. They have a built-in pacemaker. Now, we adjust the speed of our heart up and down with our physical activity, and that's done with the sympathetic and parasympathetic nervous system, 2 nervous systems that respond to sort of flight and fright or respond to very vigorous exercise. But a heart can be transplanted without any nerves, and it will pump, but it'll pump at a steady rate. It won't pump faster if you go out and exercise if you don't have these nerves,
because
but it will contract.
It's not getting feedback from the rest of your body system if those nerves aren't connected there. Now, you used what we might think of our big science word of the day, cardiac. That's a word that we would use in scientific terms to talk about the heart and things related to the heart.
Right, so that's cardiac muscle. That's the muscle of the heart. Yeah, you see, the heart could get big if it had to work harder. I mean, if we lift weights, the muscles in our arms and chest get bigger. I could rip off my shirt.
I was going to say, I can flex, but you probably can't see it through my lab coat.
So cardiac muscle is no different than the skeletal muscle in this one sense, and that is, if it has to work hard, it gets bigger. Now, we really don't want our heart to have to work hard. It works hard if it has more difficulty pushing the blood through the vessels. There could be some plaque or something clogging them that comes from our diet. There could be other reasons. Overweight can put more work on the heart.
What about an athlete? Would an athlete have a heart that's larger and stronger typically? Somebody
Right,
who's always
somewhat
exercising and
larger,
energetic?
than if just from the fast respiratory rate, the kind of muscles in the body change too. With an athlete, they get more of a certain type of muscle we call a red muscle. It's good for long distance running and that kind of thing.
Yes.
So, well, let's look at our heart. We only get one. Have you noticed that? You have 2 kidneys, 2 lungs, 2 of a lot of organs of the body. But the heart, you just get one. And that means we have to really take care of our heart. Our heart has another interesting feature. It doesn't repair. If the blood supply to the heart is interrupted, a part of the heart dies, it's replaced with just connective tissue that goes along for the ride. The connective tissue holds everything together, it connects, but it doesn't contribute to the pumping. Let's look at the heart in our model here, and by the way, his name is Algernon. And if I can just move over here a bit.
You bring in all those literary references, don't you?
I'm going to carefully remove the lungs, the front part of the lung, and the ribs. Notice that keeps you from seeing the heart. There's one little hole here you could peek through and see your heart possibly if there's some membranes in the way though. But we're going to remove this structure, which is ribs in the front part of the body.
He's got a sticky clavicle there, it looks like.
And remove the other one. And now you'll notice where the heart is located. This is unusual. It's right here in the middle of the lungs. The lungs completely surround the heart except on the back side. And on the front side, the lungs cover all of the heart except for one little piece. So the lungs are really close to the heart. You can't get closer than that. And that's a good thing because one of the things the heart has to do is get blood out to the lungs to be oxygenated. Now, rule number 1 is if blood is leaving the heart in a vessel, we call that an artery. If it's coming back towards the heart, we call it a vein. Whether that blood is oxygenated or not, if it's going towards the heart, it's a vein, away it's an artery. So here are blood vessels on the top. This blue one you might think would be a vein. It's carrying unoxygenated blood, but it's really an artery, and it's an artery going from the right side of the heart to the lung. We call it the pulmonary trunk. When vessels are very short, we sometimes call them a trunk. So let's just remove the heart here for a bit and see what's behind our heart. You can see the branch of the trachea into the bronchi. These are going to the left lung and the right lung. And in the lung, you're picking up oxygen from little sacs of air. And that oxygenated blood comes back into the heart. We'll talk about that in just a minute. The heart sits on top of the diaphragm. This little arch right here is the diaphragm muscle. That's our main muscle to breathe. When we bring in air, that muscle goes down. That means the poor heart's up here has to kind of go for a ride. It sits right on the diaphragm. In fact, it has a ligament that holds it to the diaphragm. So it's kind of going up and down a little bit as we breathe. Now imagine our heart is pumping. It's going to pump in the course of our lifetime about 1 million barrels of blood. A barrel is 55 gallons, each barrel. Now, of course, it depends on how long you live. But to give you an idea how much blood this little heart is going to pump in a lifetime, that would be comparable to 3 of these ships that carry oil across the ocean called a super tanker. 3 of those full in a lifetime. You only get one heart. So that means that your heart is inside this, we call it the pericardial area here. It's in a sac, and the heart is pumping. So I'm going to pretend that this heart is pumping, and this is the sac, pericardial sac around the heart. Okay, it's pumping away. What am I feeling against my hand right now with all this movement?
Probably a lot of friction happening there.
A lot of friction, a lot of heat. The heat generated by the heart pumping in there, just rubbing against the wall, could be fatal.
It could burn a hole in that sac.
Maybe not burn a hole, but body core temperatures could get high enough that you wouldn't be able to survive it. So, wow, what kind of solution did the Lord come up with on this one?
I bet there's something slippery in there.
You got it. You have to put some lubrication in there. And this is what the Lord has worked out for us. Where did I put my... You can't teach anatomy without a balloon.
Oh,
You
no,
have to have a balloon.
absolutely. You need balloons and tubes and all
you
kinds
have
of
to
stuff.
ignore the nozzle. Okay, pretend it's not there. And you notice this balloon is collapsed. So let's say there's no air in it. But let's say there is a drop or two of oil in here. Oh, that would make the two layers of rubber very slippery, wouldn't it, if there was a little oil that we had inside of this balloon. So we have what's called the serous pericardium. That means it's a fluid-producing pericardium, and we mentioned it's like an oil.
Yep.
And that sac wraps around our heart just the way I'm wrapping this balloon. Now, the inner layer of what would be the rubber on this balloon, we call the visceral pericardium. It's right on the heart. You can't get it off. I've dissected hearts, you just can't pick it away. It's attached. And there's blood vessels under there too. The outer layer of rubber is attached to a fibrous sac that goes all around the heart called the fibrous pericardium. And there's no give or stretch to that. In fact, it's put together like plywood. There's 3 different layers, and each layer the fibers run in a different direction. And so the outer layer of our sac attaches to the fibrous pericardium, the inner layer to the heart. Now when the heart beats, there's a slippage between the 2 layers of what is rubber here.
And that's going to prevent that friction that we'd expect.
That's right. Just think, without that, it'd be over. You wouldn't make any difference what else you had right in your body. This would be a huge problem if it couldn't be addressed. So the only problem with these sacs like this, and they're all over the place, they actually enclose all of the organs of the abdominal area. Mm-hmm. There's actually a similar lubricated sac around the lungs. The problem with these sacs is you can't run blood vessels across them.
Because the blood vessels would shear as the sac's moving and tear
imagine
through.
we punch a hole through this balloon here. That's the end of the
That's
fluid.
the end of it, yeah.
So how do you get blood in and out if you have it wrapped in a double-wall sac? Well, look, all the blood comes in at the top. At the bottom, this is all sealed off. That means when our heart beats, although the signal to beat comes from within the heart up high here, that signal for contraction has to be delayed till it gets down to the bottom of the heart here. We call that the apex, the point of the heart. And then the contraction goes from the bottom up. And that sends the blood out the top. Imagine just get that wrong. Have it start squeezing from the top down. That'd be over, huh? Well, I'll tell you, everywhere you look, the Lord's hand is certainly there. This isn't dumb luck. I hope you all know that.
So from an evolutionary perspective, there's really no way to explain how all of these pieces come together and fit together and work together the first time.
That's right. You know, people think, oh, isn't it amazing our body's complex, our eye is complex. But you see, complexity is not the whole show.
Not that important.
Complexity just simply means you sure got a lot of parts.
Yep.
This is integrated complexity. Parts working together. That's the kicker. Mm-hmm. And I don't believe evolution has a way for that. Well, that shows how the heart fits in the body. And it'll be contracting, and it's lubricated with that pericardial sac. Let's move over to a big heart. And, well, we can use a little heart, too. We'll use both of them.
He's down
Actually,
here on
each
that.
has some advantages. Here we go. If we open up this little heart, we see that there's 4 chambers. This chamber here, the one down here, I should use my stick. Here, I've got this nice stick, and I'm not using it. This chamber is called the right atrium. The one over here is the left atrium. Now, atrium, you may have an atrium on your house. It's the room you go into when you come in the front door that maybe has a clothes closet in it and a mirror and a fancy light over the top, instead of walking straight into the living room.
It's kind of an entry and a resting area, if we might think of it that way. Mm-hmm.
So this is the first chamber. On each side, left and right, is the atrium. And then the heart down here has 2 chambers. These are called ventricles. And unlike the atrium that has thin muscle in its wall, the ventricle has this really thick muscle in the wall. And notice the left ventricle over here has thicker muscle than the right ventricle. And the reason for that is the right ventricle is going to send its blood to the lung. But the left atrium will send its blood out to the whole body.
The left ventricle.
The left ventricle,
Yeah.
right. So good thing I got you here to keep
Isn't
me
it
straight.
fun to misspeak on camera all the time? I do it all the time too. No.
So you might say we have two hearts. Isn't that interesting? I said we had one heart. In a way, we have two. It's one structure, but it has one heart on the right and one heart on the left. The right heart could be considered your lung heart. The blood goes from the right heart to the lung through this pulmonary trunk here. The left heart, the blood goes through the aorta to the whole body.
Mm-hmm. So there's another big word. When we say pulmonary, that's referring to the lungs.
That's the lungs.
Scientific term for the
Pulmonary,
lungs.
right.
Mm-hmm.
So imagine if that were the end of the story, the blood from the right ventricle, or from the atrium goes to the right ventricle, and then from the right ventricle goes to the lung. What if it came back to the atrium again?
It would just keep going to the lungs, and how does my blood get to the rest of my
You'd be
body?
circling around with blood over on one side that would never get to the rest of the body. All that oxygenation wouldn't do you any good at all. Meanwhile, over here on the left side, if the left side were put together that way, its blood would go out to the body, back to the left heart, out to the body, back to the left side of the heart.
It'd get pretty loaded with waste products really quickly that are
my.
being generated in the cells.
Sadly, this can happen developmentally. Some babies are born where the blood is separate between the right heart and the left heart. Mm-hmm. It's called transposition of the great vessels. Let me show you what's involved there. If you look at the top of the heart, you notice these two big vessels coming out of the heart. This blue one is the pulmonary trunk. That's an artery carrying unoxygenated blood to the lungs, which would be over here and over here. And then the aorta is right here. It loops over the pulmonary trunk. Do you see how they're twisted, the two? There's a twist there. Without that twist, we wouldn't be here. If that was your only mistake, you just didn't get the twist. And by the way, the twist happens during the development of the baby in the womb. When that twist doesn't happen, that baby has blood going from lung to the right side of the heart, lung to the right side of the heart. Over here, blood to the body, back to the left. And that's called transposition of the great vessels. Babies survive that because there's enough leakage between the two sides of the heart to get through. Well, let's look at the chambers in the heart. This heart has doors in it. Isn't it great? We can
That's handy.
First thing we need to understand is the light blue up here is the right atrium, so the upper chamber of the right side of the heart. What is in orange here, or brown, or whatever color that is, that would be the left atrium. And there's a little piece coming off from it that looks like an ear, doesn't it? It's called the auricle, which means the ear, but it's all part of the atria. Now on the right side, the doors that we have in this model open up separately for the right atrium and right ventricle. Let's open the door for the right atrium. And notice here we have blood coming from up above. This is called the Vena Cava. This is the main vessel that brings blood, all the blood to the heart above the diaphragm. So if we look at our model over here again, can we do that? All the blood from the diaphragm up is going to, let me get here. All the blood from the diaphragm up, from this level up, is going to come into the inferior vena cava at the bottom. And all of the blood from below is coming in through the, blood from above goes into the superior vena cava, blood from below into the inferior. So we have two inlets, one pointing up, one pointing down. And you can see that in the heart here. This one points down, goes down into the body, inferior vena cava. This one comes from above, so that diaphragm is the dividing line. Once the blood is in the atrium, you really can't do much with it there unless you get it down to the ventricle, which is going to be the pump. So we open up this door, and here is our ventricle, down here. And remember, the muscle on the right ventricle isn't as thick as on the left because it only has to go to the lungs, which are right here on the side. So when this contracts, blood will then go up into this pulmonary trunk, into the lung. Now, when blood goes from chamber to chamber and place to place, we don't want it to back up. When the heart squeezes, we don't want the blood to back up and go the direction it came in.
That would do us no good. We'd be back to that same situation.
That's right.
It's just left in the body.
So when the blood is squeezed out of the right atrium into the right ventricle, you can see my probe come. Let me use the other end. You can see it coming in here. There's a valve here called the tricuspid valve. That means it has 3 leaflets. And when the heart contracts, if the blood tries to back up, which it would, into the atrium, this valve closes. And the edge of the valves have these little strings you see here called chordae tendineae. So I guess they really are strings of our heart, huh? And that keeps the doors, which are like a kitchen in a commercial kitchen that can swing both ways. That's the way this valve is. So when the ventricle contracts, you want the doors to swing and stop. And that's accomplished by these little chordae tendineae.
Yeah. So if the blood were flowing down through, it allows it to push the doors open and let the blood go down into the ventricle. And then as it starts to compress, it pulls back and those flaps close and those cords hold it from going too far and prevents the blood going back into the atrium. Absolutely. Because then we couldn't create any pressure inside the ventricle. That's another type of heart defect.
That's right. Here is another type of valve. We have a valve between the atrium and the ventricle, sometimes called the atrioventricular valve. That's this tricuspid valve. This valve is actually in the blood vessel here. It's a different design. It's called a semilunar valve, and you can think of it as three little balloons in here, half balloons, that are all facing in such a way that when the blood goes up, the little balloons open, but when the blood comes back, it inflates these little balloons that seal into one another.
Yeah.
And that's the type of valve you find in the aorta and in the pulmonary trunk. Those are actually in the beginning of blood vessels. So that has sent the blood out to the lung. When it comes back from the lung, remember we have two lungs, left and right. When it comes back from the lung, it comes back through these two openings over here. These are the pulmonary veins. And these two over here, notice it's going into this brown structure, which is the atrium. And you may say, well, wait a minute, that atrium is supposed to be over here on the side. It looks like it's on the whole back. Our heart is not sitting straight on like this. Everybody thinks, perfect heart, right atrium, right ventricular. Our heart's in our body like this, like you're a football player.
It's a little twisted in there.
Right. So when you look at the front of the heart, you're seeing more of the right side of the heart than the left from the front, because the heart's in there. And it also isn't standing straight up and down like this. It's kind of laying back and relaxing a bit. Notice that angle.
It's working so hard, it needs to relax a little.
Yeah, it needs to slope back and relax a little bit. So this is a diaphragm right down here. Okay. So the blood is going to return, and notice these vessels are painted red here. So although they are veins bringing blood to the heart, we call them, they do have oxygenated blood in these veins.
So the red and blue, now this is a big misconception a lot of people have, and we'll talk about this more in circulation in that video as well. But a lot of people think that red blood means that it's in a vein, and blue blood, or I'm sorry, the other way, red blood in an artery and blue in a vein. Is our blood really two different colors?
Yeah, as hemoglobin binds oxygen, it does change color from a more bluish color to a red color. And so we normally would call vessels carrying oxygenated blood to be arteries, but we really base it more on the direction the blood is going than whether it has oxygen or not.
And so blood is generally red. If we have venous blood, it's kind of a darker, deeper color, where arterial blood that has lots of oxygen is a bright red color.
That's correct.
And these models use these colors to help us think about the way the blood is flowing and what the oxygen concentration is.
Right. So our two big vessels coming out of the heart, the aorta is carrying oxygenated blood. That blood is returned from the lungs to the left ventricle. Now when we open this door here, we're going to see that where we had two doors over here, we just have one door here. So you're seeing the atrium and ventricle together there. Here is the line between the atrium and the ventricle right here. So the orange above it up here is atrium, the red is ventricle. And this is the only way to get through from the left atrium down to the ventricle is through this valve. This is similar to the valve on the other side between the atrium and ventricle, except this has two leaflets instead of three. And those two leaflets come together like this. And they look sort of like the hat that the Pope wears, which is called a mitre. It has two pieces that come together like sits on his head this way.
So let me guess, that's called the mitral valve.
Got it, mitral valve. Or you can just call it the bicuspid valve.
Because bi and tri, it's got 2 pieces versus 3 for the one inside the right.
And cuspid means cusp or valve.
Yeah.
And so once again, these valves are kept from allowing blood to go back up into the atrium thanks to these little strings called chordae tendineae here. And look how thick the wall is of the heart here. This has to pump the blood all the way out to your big toe. Well, the heart has its own blood vessels. Did you know that? Yeah, the heart needs blood too. And you say, well, why would the heart need blood? It's full of blood. I mean, can't it just soak out from the inside? No, the heart's too thick. In fact, we have blood vessels that are so thick, they need blood vessels.
Yes.
People don't think of blood vessels having blood vessels, but they do. They're called vasa vasorum, the vessels of the vessels. So the heart has blood vessels, and you've heard of them. Coronary. What does the word coronary or crown mean?
Sitting around in a frame.
Right. You think of a crown on somebody's head. A coronation is when you place the crown on somebody's head. So the vessels that supply the heart are like a crown. And they come out of the aorta, the very first vessels to come off the aorta, and they go either around this way to the right, or they go around this way to the left. So we have the right branch of the coronary artery, the left, they're coming out of the aorta, 2 little holes in the aorta here, and they wrap all the way around. Here you have a vein as well here. All the way around, notice there's no end to this artery. It joins the one coming the other way. Wait a minute, we have a strange thing going on here. We have 2 arteries running headlong into one another. Does that seem to make any sense?
Well, it doesn't on the surface, but it really does perform a really important function.
Yes, it does. You know that when coronary vessels get clogged, that can lead to big problems. That's a heart attack. And so we have vessels that supply the heart. This is really the most important one right here, called the interventricular, between the 2 ventricles, anterior interventricular. And they come off this ring, this coronary vessel that wraps around. If this circular vessel gets pinched or clogged anywhere, blood can get to these branches that come off from the other direction.
Going around the other way. It's like a protective system built into that.
Right. When you look at the body, you see the same thing. The blood going into your hands and into your feet go into an arch like that, so the branches that come off to supply all the toes and everything, you can stop this arch, plug it anywhere, and it still gets blood.
Gets that spread out.
So those are those wonderful coronary arteries, and of course coronary artery disease means as vessels get clogged, that part of the heart dies and unfortunately is not replaced with muscle.
Yeah.
It's replaced with
And so when we talk about a heart attack, that's typically there are lots of different types. That's a very general word. But that muscle is dying because it's losing blood supply, or it can lose nerve function and those types of things and not be able to function anymore.
That's right.
Okay.
So keep an eye out when you look at anatomy for these wonderful ring-like blood vessels.
Or in a few other places. Okay, so the human heart has 4 chambers, but if we think about other things that God's created, they have different types of hearts.
Right.
We saw a rotifer in our episode where we looked at pond water. We saw its little single-chambered heart beating. What about Claude? Claude's our pet lobster. What would his heart look like? How many chambers there?
Claude has a heart too. Most creatures have something that pumps something like hemoglobin or blood. Being an arthropod, a segmented body like this, this heart would be a single chamber. There would be lots of little blood vessels coming into the front of this little one-chamber heart through little holes called ostia. These then close up, and that one little chamber squeezes, and the blood goes out the backside.
Yeah, so it's a much simpler structure.
Right,
and then as we move into things like amphibians and reptiles and into birds, we see a little bit more complexity. And that's often used as an argument for evolutionists, that here's a chain of those things building. But we would just understand those as the way God has created those things.
You know, there's another, do we have time to cover one more little thing?
One more quick thing, I think, yeah.
There's a little ligament here, and we all have it. And that little ligament attaches a pulmonary trunk to our aorta. And when we were in the womb, this was an artery, a short artery, so we call it a duct, ductus arteriosus. And that artery took the blood that should be going to the lung, and it bypassed and sent it to the aorta. Now, that's dangerous.
But if you're in the womb, You don't really need your lungs to breathe with.
That's right. You just need enough blood to keep the lung alive. You don't need to breathe with it.
Yeah.
So that blood gets shunted over in the aorta, which is a great idea in itself, but my goodness, what happens when the baby's born? All the blood that should be going to, or most of the blood that should be going to the lung, is bypassed into the aorta. You better have a solution for this. During a period lasting about 3 weeks, a sphincter, like a purse string, takes this big artery called the truncus arteriosus, and it squeezes it until it's totally squeezed off. That then makes all the blood now coming out the pulmonary trunk here, allows it to go to the lung. And we all have this little ligament in our heart as a kind of a reminder that when we were in the womb, our mother was doing the breathing for us.
Mm-hmm. And that's another example of a defect that could happen. We would call it a birth defect or a developmental defect.
Right.
That could cause major problems
If it stays open,
newborns.
then you're wasting a certain amount of blood that should be going to the lung, goes to the aorta. That can be surgically corrected, of course.
All right, that's a lot of great factual information about the heart, but the Bible talks about the heart in kind of a metaphorical sense. It talks about it as the place where our sin is and where our feelings and emotions are. And how does the Bible describe our heart as a result of sin in Adam?
Well, of course, every inclination of man's heart, it said before the flood, was only evil continually. Think of living under those conditions. I mean, before the flood, when our hearts were only evil continuously, I don't think you could do any farming. You couldn't engage in any kind of commerce. It must have been a mess, and mercifully the Lord sent a flood that destroyed all of humankind except for 8, and we started again. Unfortunately, sin was still there. But man's heart is desperately wicked, and the Lord has to change us around through His Word and Holy Spirit. They work together in us to begin to behave, but we're not saved by our behavior. We're saved by the redemptive work of Christ. We can't keep all the laws. We can try as we may, but we can't do it.
And so it's repenting of our sins and trusting in Christ for forgiveness that we can have a new heart, as the Bible describes it,
Right.
and talks about it.
And bear in mind, it's not literally the heart that's doing all of this.
It's a metaphorical way to think about it.
If you look in the Bible, there's actually 3 different organs that are the emotional centers.
It talks about the guts, the sphincter. Yeah.
The gut and the kidneys, the rings.
All right. So we hope you've learned a little bit more about your heart. And as important as all of this is, we want to make sure that it's not just about your physical health and your physical heart you're concerned about, but your spiritual health, and that you are truly trusting in Christ and that He can bring about that heart change for you. We thank you for joining us today, and until next time, we hope you will get out and explore all that God's created for us.